Hello, everyone. This is the LEAP hip joint presentation. And during this presentation, we'll be covering the previous year's hip joint design, in addition to some potential areas of improvement for this year. To start off, here's some examples of the exoskeleton suits in action. As you can see, the hip joint lies right on the side of the user, and we'll have to deal with some significant force and torque outputs, especially when moving from the sitting to standing position and when transferring motion from one leg to another during the walking stage. And from our research, we found that the maximum torque output required of the hip joint is 80 Newton meters, which is equivalent to 59 foot-pounds force. And due to the uncertainty involved with the calculations of adding an exoskeleton with additional weight, we have upped the torque output by 1.5 to equal a maximum torque output of 120 Newton meters, which is equivalent to 89 foot-pounds force. In addition to this, the hip joint will also receive somewhere between 2.4 and 3 times the body weight in the radial direction of the hip joint. So that's the force acting onto the joint itself as it moves. And this is because when a person is moving, they'll transfer all their weight onto one leg and have to receive the full force through the hip joint. And due to not knowing the exact weight of the exoskeleton suit at this time, we've provided a large factor of safety within these forces. So this is the overall version of our hip joint. It is a little bit different because we ran into some manufacturing errors due to the cost of making this exact casing. However, the gear train remains the same. So as you can see, the hip joint also sits right outside of the user's hip and has the motor facing inward, which is another area of potential improvement since it'll have limited accessibility during practice. And it could potentially interfere with interfacing with the lower back of the exoskeleton suit. So for our design, we have the overall dimensions of 9.5 inches running from length, 6.5 in terms of height, and 6.3 inches in width. Now moving on, this is the internal view of the hip joint. So this has a total gear train reduction of 300 to 1, which essentially means every time the motor rotates 300 times, the output disc here will rotate 1 time. And we have also met our target of 120 Newton meter output. To give a quick little overview of how this gear train naturally functions, we see the motor will rotate into the pre-bought planetary gearbox right here, which has a reduction of 16 to 1, which then transfers to the spur gears, which has another reduction of 3 to 1. And as the spur gears rotates, it transfers into the planetary gear. So this primary shaft is called the sun shaft, which has its next gear right in here, which is called the sun gear. The sun gear will then transfer to the planetary gears, which has a couple of large advantages, which are previously mentioned in Yotam's video. But the force transmitted is significantly reduced since it's distributed fully around the sun shaft, which allows for the forces to cancel out and reducing the stress on the gearbox itself. This will then interface with the ring gear within the planetary gearbox to have its final gear reduction. And then finally, the output shaft will then be rotated. This output shaft currently has 120 degrees of rotation. However, it's theoretically capable of rotating a full 360 degrees. And then this output shaft is then connected to the linkages, which is also the rest of the leg. So now moving into a more internal view, We have the Maxon motor, which is the EC motor, and a coupler, which is connected to the Maxon motor, since the output shaft of the Maxon motor is not of the same diameter as the input shaft for the planetary gearbox that we pre-bought. This is also a low point of stress, since torque from the motor is fairly low and will become increasingly high as we move through the gear train. So this point is of fairly low concern. The spur gear has a modem of 1.5, which is essentially the number of teeth divided by the pitch diameter, and has 32 teeth altogether within this output spur gear in the first stage. The second stage of reduction, seen on the right, has a spur gear interface with the first stage, moving on to a planetary gear set, which is a parallel, what we call parallel planetary gear train with a constant modem of 1.5, which then travels to the output carriage, or what I call the output disc. So now we'll look at the gear reductions within each stage. So moving from the motor to the self-bought or pre-made gearbox, we have 16:1. From the gearbox to the sun shaft, we have 3:1. And to the planetary gears, we have 6:1. So this becomes a total gear train of 288:1. And with the assumed 98% mechanical efficiency, because as the gear train moves, there are certain losses with each gear interfacing together. So that will then reach our desired output. So as you can see on the right, we can show the approximate torques as we move through the gear train itself. So with the motor output shaft, we have 0.51 Newton meters to the gearbox output of 8.2, sun shaft of 24.6, planetary at 16.4, and then there's 3 of these, so it's 3 times that, equaling to the required output of 148 Newton meters. And then when we account for the 28 Newton meters of loss, we reach our desired output of 120 Newton meters. So this is more of an in-depth view of the planetary gear set itself. So as I mentioned, the primary shaft or sun shaft sits in the middle, which transfers motion from the sun gear into the planetary gears, which interface with the ring gear here. And then, these bearing outputs then mate with the carriage or output disc, seen in blue on the right. So this, we don't need to spend too much time here, but this is how we calculate for the reductions within the planetary gear set. These equations were found online and verified within talking to professors and going through our design reviews. I won't get into the details here, but this is a proof of concept for how our planetary gear operates. Some more details here, where we also incorporate our expected losses while transmitting through. So with a gear train loss, it'll be a loss in speed, which equals to a higher torque output. So now I'll be delving a bit into depth on the governing equations on how we perform the analysis on this gearbox. Because with exoskeletons and having a human user, it's very important to verify that our gears and our hip joint will be able to deal with having a user and having the appropriate factors of safety. So in general, when we're designing for an exoskeleton, we want a factor of safety of 4.0, which essentially means that we want our system to be able to do a 4 times what we expect it to deal with. In this case, we have a factor of safety of 1.5. However, we have our gears designed to meet an infinite life requirement, which is much more conservative compared to a standard factor of safety calculation. So starting here on the right, we're going to look at the gear stresses. So this equation seen right here comes from the AGMA, or American Manufacturing of Gear Associations, which also follows the International Standards Organization, which essentially ensures that the equations we're using follow standard practices and meet all the requirements possible. So sigma here, which is the stress, has 4 components here, where we have kV, the velocity factor, Wt, the tangential tooth load, which is the force transferring through the teeth, F, which is the face width of each tooth, is how wide each tooth is, and the module, which is the, as I previously mentioned, the number of teeth divided by the pitch diameter. And Y is the Lewis form factor. All these equations can be found in your local Shigley's textbook, which any of the upper division members can be able to easily show you how to get access to. I believe we have a PDF within our Google Drive. And now these are each of the ways that we calculate each factor within the equation for stress. So without getting into too much detail, these are all the equations found and have been verified not only by professors, but through our own personal research, which is how all of these processes get started. I think it's also beneficial to look through all these definitions with all these different variable names. However, ultimately, we have factors of safety of 5.4, 6.4, and 10.5, which are well above the required factors of safety, which leaves plenty of room for future design iterations to reduce size of our system overall. So moving into more detail, we have to show the gearbox rating, meeting well above standards for factor of safety. And as you can see here, these are references to the figures of and equations within the Shigley's textbook. This is another tool used for general practices. So if you have a RPM and the number of teeth, it will give you the approximate torque rating that each gear will be able to handle for, and in this case, it is spur gears, since we do not use any helical, worm gears, or anything like that within last year's hip joint design. And this also verifies how our factors of safety are well above the 1.5 requirement. Now moving into the shaft analysis. These shafts have to deal with not only the direct loading, but also have to account for stress concentrations. Because whenever you have a shoulder within your shaft, or whenever you have a keyway, which holds the gears in place, you will have to account for that, since sharp edges and changes within the standard cylindrical shaft will have additional stresses. And this little figure on the right highlights the Excel sheets that we created in order to optimize the design process. So within this Excel sheet, you can change the shaft diameter and it will pop out the factor of safety based off any change within shaft size, positioning. This little free body diagram right here is fully customizable. So you can change the face width, you can change the location of the gears, you can change the location of the shoulders and the bearing locations. It's an incredibly useful tool, and I recommend that everybody performing design work in general and in this club creates an Excel sheet which prevents future rework. Because something we'll find out really quickly is that you'll think you have the right design made and made all the right calculations, but then someone will point something out and you'll have to completely change your design. So instead of having to rework your whole analysis, you can simply just change it with an Excel tool. One thing I'd also like to caution is it's always a great idea to do one version on hand because Excel sheets can be a little finicky sometimes. So you want to make sure that your Excel sheet's working properly before using it to verify your design. These stress equations on the right, or sorry, on the left, they are all AGMA-based stress equations. So they account for stress concentrations and they follow all industry standards. And here's the results of our shaft analysis. So with the motor exit, we have a factor of safety of 11.4, simply because it has a very low torque load. The gearbox output, especially within the key stress concentration points, the keyway and pinion, they have the keyway for the pinion, sorry, has 7.5 within the sun shaft, which is right here. The shoulder has a stress concentration of 8.8, and the shoulder is when you have a sharp diameter change within your shaft so that the gear can rest on that shoulder and not have to worry about sliding out of place. And then the keyway, which I previously mentioned, holds the gear from not just spinning freely on the shaft, holds it, which actually has a kind of pin and groove to allow the force to transfer easily within the shaft. And as with the planet shafts, they also have a very high factor of safety because the load is such evenly distributed within the planetary. As you can see in later slides, or it might be in the appendix, we show the free body diagrams, which verifies how the loads will cancel out within the planetary gear. And as with any stress concentration, we have keyways. So this is the actual key itself. So on this free body diagram, you can see it's purely shear stress acting on the keys, because one force direction will be coming from the gear and the other one will be coming from the shaft, which will then induce the appropriate torque that we previously mentioned within this presentation. I won't go into too much detail on this aspect. Oh, sorry. And then we also have to analyze the bearings because the bearings also have ratings, but we have different loadings within our bearings. So we have to go through back to our Shigley's textbook and find the right stress concentration or stress calculations. So this verifies for each bearing used that I'll be able to extend 5.71 times 10 to the 8th cycles, which is well above what we expect to use, especially within a prototype. So some other things that are important to consider when designing the hip joint is tolerance stacking. So as you keep on designing your gears, your bearings, your keyways, your shoulders along the length of a shaft, if your tolerance on each section is not done appropriately, they will continue to stack up. So in like an extreme situation, you could see that your farthest gear is off by 0.5 or 0.05 inches, which would completely deteriorate all the stress calculations we've done previously. Another thing to consider is shaft alignment, because if you have any shafts that are askew from the appropriate true position, that'll cause the gears to not engage properly, which will cause additional stresses within the gears. Axial loading along the linkages or radial loading is something I mentioned early on within this presentation. But that's another thing that needs to be considered within the hip joint design. In this case, we have a Durling bushing acting on the output shaft or output disc / carriage, which then transfers the load from that output disc to the outer Durling bushing, which is connected to the casing itself. Which brings me to the loading and stress within the gearbox casing. So this is something that we did fairly poorly, to be completely honest, last year, since we ran out of time. And due to the irregular geometries within the casing, this can lead itself to be a finite element analysis problem, which can be very difficult and time consuming. So this is something to definitely take into consideration when designing the hip joint. For example, all the loading on each shaft will have to be transmitted through the bearings on each end to the casing. So the casing will receive stress concentrations due to the bearing loading. If the legs were to kind of move inwards, then that would create a transverse loading during walking, which is another potential risk and needs to be accounted for. So within the previous design, we have the output disc sitting on a carbon fiber casing, which will prevent it from transferring its load into the oblivion and providing it adequate support. Another big thing that we ran into last year was manufacturing costs. This is something to always keep into consideration. Going into spring quarter, we had a design that needed to be CNC'd due to the high tolerances with shaft alignments and making sure your bearings are in the right place. However, we later found out that this was going to cost us like around, I think it's $1,500, which would well exceed our budget and almost mirror the exact cost of the hip itself. So that became blatantly obvious. So we had to make some last minute design changes to adjust the casing in order to be both functional and cost effective. Another thing to consider is when you have the gearbox assembled, and since we're manufacturing the cell ourselves, there's going to be some more tolerance within the gears and a little bit more slop, which means the gears aren't perfectly engaging, which can cause backlash when you're driving the hip joint. So that is essentially a slight delay whenever you try to rotate the gear in a new direction. So if you're going counterclockwise and then change it to clockwise, there will be a delay due to the backlash involved, which can be accounted for within controls, but it's something that needs to be considered within the design process. And finally, considering how the hip joint will be attached to the linkages and to the lower back section of the exoskeleton. The lower back of the exoskeleton has not been designed at this time, which is another area for people to work on, but you need to consider how is this going to be attached, how will it be removed for maintenance, because after extended wear and usage, it will need to be removed, disassembled to some degree, and then repaired if any repairs are going to be necessary. So for future design iterations, there's a couple of choices. As I just expressed throughout this presentation, there's a lot of room for optimization of the existing design to both reduce size, weight, and costs. Primarily size and weight are the primary interests. As you saw previously, that there are large factors of safety that are well exceeding what is necessary. So there's potentially room for improvement there. As I just discussed, manufacturability is key, and the current design we're able to manufacture, but it's not as load bearing as the original design. So looking into that would be another great area of improvement. Integrating this design with a new lower back would also be a great option. And one thing that we definitely need to integrate if we go into a completely new hip joint or even continue to work off of this existing hip joint is integrating robust hard stops. So that means that the leg will only be able to travel a certain range of motion. And once it reaches here, it is physically impossible to travel further, which could prevent breaking their leg, for example. and potentially pursuing a completely new gearbox design, which can solve all these issues above if done appropriately. And I encourage you to reference Yotam's gearbox presentation, which outlines a couple of really great choices. Now we're kind of getting more into the appendices, but I'll just run through these quickly for if anybody wants to pause the video and take a closer look. Showing the free body diagrams for the gears interfacing. And this is what I was showing, how the gears will all cancel out within this gearbox. Same with the planetary and the output shaft, which only leaves the resulting torque that is transferred within the output. Another thing to mention is this is the Durling bushing that I was talking about previously, this curved and blocked off section, in addition to the inner Durling bushing, which is adhered to the output disc. These are all seen in blue as the spacers that separate the gears. We decided to go with spacers because they do not require retaining rings, which are essentially small, shallow cuts into the shaft where you can put a little small ring around to make sure that the gears don't slide back and forth. So within last year, we simply 3D printed these. However, they're prone to breaking and are not load bearing. So looking into getting a new material and a new way of manufacturing these would also be another good area. This is the motor spec sheet. You can see highlighted in orange right here is the motor that we actually selected. And you can look into this at your free time. This is the aforementioned hand calcs. You can see it's a whole lot, but this is just how we verified that our Excel sheets would work, and we left them in variable form to allow for future design changes without having to completely rewrite our sheets, Excel sheets. Shows more of a dimensional breakdown. I believe this is the planet shaft. Yes, this is the planet shaft, which is the one that circle around in a group of 3 around the sun shaft. Some more Excel sheets. This is for the planet shaft as well. And then this is shaft analysis. So this is where we are accounting for bending within the shaft. Since you have multiple different types of loading along the length of the shaft, we're making sure that there's not going to be too much deflection along the length of the shaft. So within here, this top chart, we see the moment acting on the shaft along the whole length of it. So in this case, the shaft's total length is 65 millimeters, and this is the resulting deflection. So we have a maximum deflection of 0.045 inches, or sorry, millimeters, which is incredibly small. Some more miscellaneous sun shaft analysis calculations. Also verifying that the radial loading through the output disc will not cause significant deflections within the sun shaft, as the load is transferred from the output disc or carriage through the planetary gears to the sun shaft. Some more additional calculations that have verified that our torque losses within the Durling bushing or the support bushing on the output shaft which we accounted for previously, motor shaft analysis. So that's the output shaft of the motor. Some more pretty pictures. And this is some feedback that we got. All right, thank you for your time.